Good morning, everybody. Thanks for coming to the seminar of the group of Campus e Particula at the Universidad Nacional de Colombia in Bogotá. It's a great honor today to have as a speaker Professor Alberto Salvio from the Physics Department at the University of Rome Tor Vergata. Professor Salvio obtained his PhD from SISA in Trieste and holding research and teaching positions in various institutions in Switzerland, Spain, Italy, and at CERN. Professor Salvio is a staff member at the Physics Department at the University of Tor Vergata since October 2018, teaching high-level courses of particle phenomenology, in particular with methods of thermal field theory, author of almost 100 publications with thousands of citations. His work has great impact in theoretical physics of fundamental interaction. Today, he will talk about supercooled phase transition with radiative symmetry breaking. Please, Alberto, 1 hour.
Okay, and thank you very much for the invitation and for the very kind introduction. So this talk is mainly based on a series of publications, some of which are in collaboration with my PhD students Francesco Rescigno and Filippo Cutrona at the University of Rome Tor Vergata. So my talk will be about phase transitions in a scenario where symmetries are broken and masses are generated radiatively, so with some radiative symmetry breaking with corresponding generation of masses, because in this scenario, one always has first-order phase transitions. We'll come back to this point in the bulk of the presentation. And a motivation is that this kind of phase transitions, first-order phase transition, lead to observable gravitational waves and primordial black holes that can constitute at least a fraction of dark matter. Furthermore, an interest in first-order phase transition comes from the fact that this would signal new physics because cosmological first-order phase transitions are not present in the standard model. Now, one thing I would like to stress from the very beginning is that a radiative symmetry breaking it can be a feature either of standard model extension, in the sense that a standard model is extended in a way that symmetries are broken radiatively rather than with tree-level effect, just like in the standard model, pure standard model, or can also alternatively be a feature of a dark sector, which is weakly coupled to the standard model. In this second case, the standard model would be the one we study in textbooks, but will be weakly coupled to a sector that is classically scale invariant without masses at the classical level, and then the symmetries are broken radiatively and masses are correspondingly generated. So this is just a spontaneous symmetry breaking, but does not occur at tree level, but through radiative corrections. In the talk, we'll discuss a model-independent approach that can describe these phase transitions in this scenario of radiative symmetry breaking that is valid for large enough supercooling. The phase transition will start being effective at a temperature that is much below the scale of symmetry breaking. And also a plus is that it can be implemented perturbatively. And this can quantitatively describe phase transition in this scenario, in terms of few parameters that can be determined once the model is specified. So we will treat these parameters. We'll go back to this content here and define the parameters explicitly, but we can treat these parameters as free parameters in this model-independent approach. Further advantage of this scenario is the predictivity, because masses are zero at tree level, so we only have marginal operators, so we have less free parameters. Now, let us summarize what is radiative symmetry breaking, which was first studied by Coleman and Eric Weinberg, and then generalized by Gilden and Steven Weinberg later on in the 70s. So one starts from a classically scale invariant theory. So if we focus on gauge fields, scalars, phi a, and fermions psi j, the most general Lagrangian is the one that is written here. I will use just real scalars for parameterizing scalars in general without loss of generality, and I will use Weil fermions to describe fermions in this general theory. Then I will have a generic Yukawa coupling and a generic quartic coupling, which preserves scaling invariance for the scalars. And this lambda A, B, C, D are the quartic couplings. This Y, A, I, J are the Yukawa couplings. This FA are the field strength. This d mu are the covariant derivatives, so standard notation. Now, in order for the radiative symmetry breaking to occur, what we need is the presence of some flat direction at tree level. In the RG improved tree-level potential, at least. Why is that? Because we have to have a dominant behavior contribution of radiative corrections, and this can only happen when we have some tree-level flat direction, because otherwise we will lose the validity of perturbation theory. So there must exist some energy scale that I call mu tilde here, at which the no-scale potential, VNS, develops some flat direction. And I can parameterize this flat direction with the unit vector in the scalar field space. So some nu that satisfy this condition. I always understand summation with repeated index. And chi is some real scalar that tells us where we are along the flat direction. So the RG improved potential V along this flat direction, nu, is given by a simple quartic coupling, where this lambda chi is given in terms of generic quartic couplings lambda ABCD by this relation here. And the fact that we have a flat direction at mu tilde means that lambda chi vanishes at that scale. Now, if we include the one loop correction to the quantum effective potential, we end up with this expression here, where beta bar is the beta function of lambda chi at mu equal to mu tilde. Chi 0 is the symmetry breaking scale, and it is related to mu tilde through a renormalization scheme dependent relation. So the renormalization scheme dependence is some kind of bird inside this definition of chi 0. We have already said that the lambda chi at mu tilde equal to 0 corresponds to the presence of flat direction. We also have to impose that beta bar is positive in order for chi 0 to be a minimum of the potential rather than just a generic stationary point. It's always a stationary point. If you also require beta bar to be positive, it is also a minimum. Now we can consider the fluctuations of chi around chi 0, and this will represent some particle with a relatively small mass, because the mass is set by the beta function is given by this equation. So since the beta function in the perturbative regime is at most of order 10 to the minus 2, this will be slightly below the scale chi 0. So it predicts some light scalar. Also, chi 0 different from 0 can break, we always assume chi 0 different from 0, can break global and or local symmetries and generate the particle masses. For example, if we include in the Lagrangian a term of this form, some quartic coupling between chi squared and h squared, where h is the Higgs doublet, this will trigger electroweak symmetry breaking. So as soon as we set chi to its minimum chi0, you see that this will generate a tachyonic mass if lambda chi h has the right sign, and so you will trigger electroweak symmetry breaking. This scenario was proposed as an alternative to the Higgs mechanism tree level in the standard model, but it is realized now that this is not viable in the pure standard model because, well, because of this relation essentially. So the fact that if you have just one scalar, the Higgs in the case of the standard model, this will be too light essentially to be viable because it's suppressed by a beta function. However, it can well be that the standard model is embedded in some extended model that features this radiative symmetry breaking with some more scalars that can be relatively light if chi0 is sufficiently larger than the electroweak scale. Okay. So on
So,
top,
excuse me, in this case, we don't have anymore the problems to have a minimum outside the perturbation theory because the the number of the fields is more than one, and so one can select a flat direction. Instead, usually with the usual Coleman-Weinberg, one has corrections that bring the minimum outside from the regime of the perturbation theory. So one has to improve the effective potential. But the fact that one select one flat direction eliminate this problem, or eliminated
yeah, if you don't require the presence of the flat direction, as discussed in the paper by Coleman and Weinberg, then you have a kind of breaking of perturbation theory. You cannot describe this minimum within perturbation theory. There is some one-over coupling essentially appearing in the equations as discussed by Coleman and Weinberg. Yeah.
But here, I mean, with having a flat direction, the minimum where you find the mass is purely coherently in perturbation theory. You
Yeah.
don't have
Yeah.
any trouble with
Yeah, as
even
long as, of course, the couplings are small, otherwise this doesn't make sense.
Of course, of course, but we just with one field, even with the small coupling, you got the impossibility. You don't get this
Oh, I see what you mean.
symmetry breaking.
I see what you mean. You mean that if you just have chi and nothing else,
Ah, ah,
okay. So this is even more minimal than standard model. Just one field, then
one field.
yeah, you have problems, and this is the reason why Coleman and Weinberg introduced a gauge field. Yeah, well, you can also see it from this condition beta bar positive, because if you just have this field, then beta bar will be set just by lambda chi, but lambda chi is zero at mu equal to mu tilde, so it will be zero beta bar. So also to make beta bar positive, it is important to introduce other fields. Okay, this is not a big problem because, okay, we are at least have the fields of the standard model. But even in the standard model, as I was saying, this is not viable in pure standard model because it predicts a too light Higgs essentially.
Mhm.
This was also
And yes, and in this VQ, there are essentially two kind of one loop correction. I mean, there is a one loop correction that provide the improved effective potential with the running coupling constant, plus the loop correction that provides
Yeah, yeah.
Mexican hat
Yeah, in
with
fact, here in general, you will have also before this beta bar fourth, here you have plus essentially this contribution here. But this is zero because you are expanding around mu tilde.
around. Okay, okay, okay.
So you just have this
Mhm.
contribution.
Still, everything is unimproved effective potential.
Yeah, yeah, it's it's expanded
There-
around mu
It's
tilde.
is resummed in by the renormalization group.
Mhm.
Okay.
Okay, so on top of that, you can also add thermal corrections. Here I show the one loop thermal correction, which is proportional to the temperature to the fourth, T to the fourth. And here we have the thermal functions, JB and JF, that are defined by these relations. And also I put a small x expansion for the argument of the thermal functions being small up to some order because this will be useful for the later discussion. Also here MB and MF are the background dependent bosonic and fermionic masses, and NB is 1 if you have a scalar, is 3 if you have a vector boson. Also, I'm adding some contribution to have the observed dark energy, but this will not be very important in the next slide. The one important thing I want to stress here is that the phase transition associated with radiative symmetry breaking always turns out to be of first order. If you have this structure, you can show that the potential has this behavior at very large temperature. There's no symmetry breaking. And then when you lower the temperature, at some point you reach some critical temperature where you have the degenerate vacuum. And if you lower even more the temperature below the critical temperature, you get another minimum, which is separated from the symmetry preserving minimum by some non-vanishing barrier, which means that the phase transition is of first order. So there must be some thermal or quantum jump between the false vacuum, the symmetry preserving vacuum in this case, and the true vacuum, which symmetries, because basically chi will be non-zero here. Okay, so to compute the decay.
Excuse me, these MBMF are the thermal masses. I mean, they are temperature dependent.
Well, in this expression, they are just the background dependent masses. Okay.
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 And but I mean, they are I mean, they are
Well, this is
masses
just a one loop correction. So if you divide with an association group, you get a correction which is higher loop,
higher order, so
higher
it is
order.
coherently renormalization group invariant.
Mhm.
Okay.
Okay, so to compute the decay rate per time volume that I will call gamma is important to determine the probability of tunneling between the false and the true vacuum, we can then use the formalism introduced by Callan, and then generalized to finite temperature by Linde in the 80s. Now, one important feature of this scenario and these phase transitions occurring in this scenario is supercooling that I've already introduced before, but let us be a little bit more specific. As long as perturbation theory holds, for all radiative symmetry breaking theories, when T goes below the critical temperature, the scalar field chi is trapped in the false vacuum until T is much below Tc. So it is much below chi0 because Tc turns out to be parametrically of the same order of chi0 because that is the scale in the problem. In other words, the universe features a phase of supercooling. this is the statement that the supercooling is there, and was first observed by Witten in the 80s in the standard model with radiative symmetry breaking that I mentioned before, that then turned out to be phenomenologically excluded, but in the 80s was not clear whether this was viable or not, whether some light Higgs was viable or not. So Witten studied this model and the phase transitions in this model and found that there is supercooling. Actually, this is a very generic property of this scenario, not only a property of the standard classically scale invariant standard model, but a generic property of this classical scale invariant scenario can be explained in the following way. If the theory is exactly scale invariant, then gamma v should be proportional to t to the fourth. There are no scales, only temperatures, so gamma v is the dimension of energy to the fourth, so it must scale as t to the fourth. But we know that high temperature symmetry is restored, and gamma v has to be positive, of course. So when you lower the temperature, if it's zero at high temperature, it must be zero also at low temperature. So there's no transition. But in this scenario, scale invariant is only classically at work. And it's a good approximation if perturbation theory holds, but not exact. It is not an exact property. At quantum level is broken. We have already seen how potential is lifted. The fact that we maintain perturbativity, we'll comment about perturbativity in a few seconds, but the fact that we keep perturbativity basically tells us that this quantum breaking of scale invariance will be just logarithmic. But the logarithm varies very slowly, and so it is only when the temperature goes many orders of magnitude below chi0 that gamma v can start being effective and sizable. And so this means that you should expect always some supercooling in this theory. Now, perturbativity, of course, requires more couplings, but even if you have small couplings, Linde pointed out that in some massless theories at finite temperature, you have still a breaking of perturbation theory, essentially because the thermal masses become bigger than the quantum masses at zero temperature masses. But in this case, this is not the case because of supercooling, the fact that the temperature is much, the phase transition starts being the zero temperature mass is typically much bigger than the thermal because there is some, to some extent, but we don't know how much. There are models in which there's more supercooling, others in which there's less. But if not supercooling occurs, which is possible, the amount of supercooling needed is quantified by this parameter that is called epsilon, the sort of collective coupling of chi to the other field. It is defined by this relation. It is chi independent. If because MB in this case, when epsilon is small, you can approximate the just terms. Essentially, this term here from the comes from the quantum effective potential that I showed you before. And the first term here, the quadratic one, comes from the expansion of the thermal functions truncated at the leading x, the argument of the thermal function. Because it turns out is small, you can use this small you can stop at first temperature by this relation, and lambda is defined in terms of beta bar and chi0 by this other relation. Lambda is positive, m squared is positive. And also at the leading order and first approximation, gamma v can be written in this way, in this scenario, where S3 is S3 over T is the action of the so-called bounce, which is the solution of this configuration. Sorry, is the time-dependent is a time-dependent configuration, which is a solution of this equation with these boundary conditions. Also, the action can be simplified and written in this term, in this way. With some scaling argument. Of course, the action in general will have the kinetic term and the potential term, but when you when you evaluate on the bound solution by using some scaling property, you can write it in this way. In principle, there can be also time-dependent bounces, but it turns out that if you use perturbation theory is valid, so G cannot be large, it can be at most of order 1, then it is the time-independent bounce that dominates the transition, and so you can integrate over time and get the action equal to the three-dimensional action divided by the temperature. This one of the temperature comes from the integration over time of some time-independent configuration. And this is the final result for this effective potential for the three-dimensional action. It is proportional to m over lambda through a proportionality factor that turns out to be this number approximately. You can compute how many digits you want. Basically computing the bounce for some fixed value of lambda. For example, here you can see the time-independent bounce for lambda equal to 1 divided by m. And also here you can see the integrand function appearing in S3. And so you can evaluate this term. So the action is very simple in this approximation. This is the leading approximation. If epsilon is small, this is the leading approximation. Now you can start computing corrections in a small epsilon expansion, essentially including more and more terms in the small x expansion of the term functions that we have seen before. And we will call this expansion a supercooled expansion, essentially, because epsilon small means that you have a lot of supercooling. If you go back to the expression of epsilon, you see that there is a logarithm here. And when t becomes really tiny with respect to chi0, exponentially tiny, then this is suppressed. Okay. So you can also compute what is called a nucleation temperature. The nucleation temperature is the temperature at the time called nucleation time when the gamma v equals the fourth power of the Hubble rate corresponding to the physical situation in which the field is trapped in the false vacuum. And so you have some potential energy difference between the true vacuum, which corresponds to the universe where we live, and this false vacuum. So since in the universe where we live, the cosmological constant is very small, is negligible for the scales, then when chi is trapped there, the system feels some cosmological constant and so exponentially expand at a rate given by the argument of this fourth power, that is hi to the fourth. And it is given in terms of the parameters that are introduced and the reduced Planck mass by this relation. Now, when the temperature is above this nucleation temperature, what happens is that gamma v is smaller than hi to the fourth. And so the phase transition, first of all, the phase transition creates bubbles, but in this case, they are diluted by the expansion of the universe. when the temperature drops to the nucleation temperature, this effect is no longer there. I mean, the rate of production of bubbles is sufficiently high that the bubbles are no longer diluted by the expansion of the universe. That's why this parameter Tn is so important. And in the approximation that I showed in a previous slide, Tn is given by this relation here in terms of chi0 and these new parameters that are defined in terms of the previous parameters by these relations, A prime and C prime. Now, one always has a very strong phase transition. The strength of the phase transition is a parameter alpha that is defined in terms of this ratio, where delta V is precisely the difference in energy, potential energy density between the false and the true vacuum. And rho r is the radiation energy density. This ratio is evaluated at t equal to Tn. Now you can rewrite this expression in terms of the fourth power of Tx divided by Tn, where Tx is the temperature at which the potential energy density, delta V, equals the radiation energy density. And so it is expressed, it can be shown to be expressed in terms of the fundamental parameters that I showed you before and the number of relativistic degrees of freedom G star by this relation here. Now, this is always much bigger than 1 because of supercooling, because Tx is essentially of order chi0, maybe a little bit below, 1 order of magnitude below typically, because beta bar is a beta function and G star is at most 100 or 110 in standard model. So this Tx is kind of 1 order of magnitude below chi0 typically, but still is not many orders of magnitude below, and so this ratio is always much bigger than 1, and you have a very strong phase transition. The parameter alpha, the center of phase transition, is always quite big. Now, you can also compute another parameter, the inverse duration beta of the phase transition, which is the time derivative of the logarithm of gamma v, computed at the nucleation time. And in this approximation, you get this expression here in the supercooled expansion of the leading order. This tells you how fast the phase transition is. If beta is small, the phase transition is quite slow. If beta is large, it's quite fast. Okay, but again, corrections can be easily computed in a supercooled expansion. This is just a leading result in the supercooled expansion. Now, epsilon very often can be instead of order 1 in typical models. So it is important to extend this treatment also to the parameter space where epsilon is of order 1. And there are two cases, a simple case and a more difficult case. Let's start with a simple case, which is the following. When you have several degrees of freedom with dominant couplings of the same order to chi. And in this case, it can be shown that even for epsilon of order 1, the leading order approximation in small x expansion of the thermal functions still is valid. And so the formula we have seen in the small epsilon case still hold. However, this is not the general case. Sometimes we have, for example, one field that has a dominant coupling to chi and all the other fields with negligible couplings to chi. In this case, for epsilon of order 1, the previous approximation breaks down, and you also have to include a cubic term in the effective potential, which appears here. Which comes from the term x to the 3 alpha in the small x expansion of the bosonic thermal function. And this k is defined in terms of g tilde and t by this relation, where g tilde is this new effective coupling of the chi to the other fields, only bosonic fields, because the x to the 3/2 term only appear in the bosonic thermal function. Okay. So now you have to extend the calculation of the bounds to the presence of this cubic term. Again, the bounds equation would be the one that I showed you before, but now you have a cubic term. When you put the solution inside S3, again, you can use the simplified version of S3 computed in the bounds that I showed you before, but now in the effective potential, you also have a cubic term, so there will be a cubic term in the integrand, where this phi is now a dimensionless field, defined in terms of chi by this relation, and lambda tilde is related to lambda m and k by this relation. It is also positive, like lambda. Now, it is no longer sufficient to compute the bounds just for one value of lambda, but lambda tilde now becomes a significant parameter in the bounds equation. So, for example, we can start computing the bounds for lambda tilde equal to 1, which is the one that is shown here. Again, this dashed line corresponds to the integrand of S3. But this is not sufficient. You also have to vary lambda. It turns out, lambda tilde, sorry, and then turns out that for large lambda tilde, you go back to the previous case where epsilon is small. So we are mostly interested in lambda tilde around 1 in this case. And so here I show the bound solutions for lambda tilde between 1/2 and 3/2 with steps of length 1/10. And the maximal height of the curves here increases by decreasing lambda tilde to give you some idea of how the bounces look like. Now, this is some sort of first approximation when epsilon is of order 1, because you have included the leading terms in small x expansion thermal function plus this x to the 3/2 term in the thermal function for bosonic fields. But there are also all the other terms. These are small corrections when epsilon is of order 1, but they are not 0. So you can improve these estimates by including more and more terms in the expansion of thermal functions for x around 0 and compute everything in and improve the supercooled expansion. So the difference between supercooled expansion and improved supercooled expansion is that in the improved supercooled expansion, the cubic term is treated non-perturbatively in the calculation of the bounds, while all the other terms in the small x expansion of thermal functions are computed perturbatively. While in the supercooled expansion, even the cubic term is treated perturbatively. Okay. And now in the improved supercooled expansion, you can also compute the nucleation temperature. Now it is more complicated because you also have a cubic term, and you can determine the nucleation temperature by finding the solution with respect to lambda tilde of this equation here that we call lambda tilde n. Once you know lambda tilde n, then you can extract the nucleation temperature. And the A1 and the A2 are defined in terms of the previous parameters by this relation. So now you can compute this solution by varying A1 and A2 once and for all, but numerically. I mean, I was not able to do it analytically. It is a quite complicated equation. So I computed numerically. And here you have a three-dimensional plot. Here you have a contour plot for lambda tilde n. And the inset here represents the maximum value of A2 for A1 fixed, for which you have a solution. Okay, because there isn't a solution for any A2. There is a maximal value for A2 for which there is a solution. Okay, now you can also compute the inverse duration in terms of this function f of lambda tilde that is defined here. The inverse duration is given by the derivative of that function multiplied by, the derivative is negative, so putting an extra minus becomes positive. And here also the other parameters that I've introduced, gg tilde and beta bar, appear. This is how the inverse duration looks like divided by Hn. Hn is the Hubble rate at the temperature equal to the nucleation temperature. That's why I put an N. And here I give you the inverse duration as a function of the parameters g and beta bar by varying chi0 from chi0 GV scale, or a little bit below, up to 10 to the 12 GV. And here I have the corresponding contour plots. Here, for simplicity, I put G tilde equal to G. But okay, you can do a more general analysis. Of course, when you start being more general, you want to include more and more models, you want to improve this approximation, more and more parameters appear. So you become more general, but you pay the price of having more parameters. And so you essentially are not that model independent anymore, but still, I think this is an interesting result. Also, I'm in the plots, I'm setting epsilon less than 3 because I know that at some point, when epsilon becomes of order 10, this approximation is no longer valid, and you have to include other terms in the expansion of the thermal functions with respect to their argument. Now, gravitational waves. I said that phase order phase transition predicted gravitational waves. The spectrum of gravitational waves, omega GW, as a function of the frequency f of the gravitational wave, is defined by this relation where rho critical is the critical energy density, which is defined in terms of the reduced Planck mass and bar PL, and the present value of the Hubble rate by this well-known relation. And rho GW is the energy density carried by the stochastic background. Now, in our case, the dominant source of gravitational waves are collisions of bubbles of the new phase inside the background of the old phase, the false vacuum. And because of that, the gravitational wave spectrum is approximately given by this relation here, where HR now is the Hubble rate computed at the reheating temperature. So after inflation, because when the field chi is trapped in the false vacuum, the universe, as I said, exponentially expands, so it inflates. After inflation, temperature drops by many orders of magnitude, then you need reheating. So you should reheat the universe up to some temperature, which is called the reheating temperature, and this HR is the Hubble rate computed at the reheating temperature. And f peak is the frequency peak of the gravitational wave spectrum that is also fixed in terms of beta over HR and T reheating and G star of T reheating. Now, if reheating is sufficiently fast, which essentially means that the reheating temperature equals what I call TAQ, the equality temperature, when the temperature was such that the vacuum energy density equals the radiation energy density. At that temperature, when the T reheating is equal to that temperature, then you say that the reheating is fast. And if this is the case, then HR can be approximated by HN. It can be shown. And so you can use the previous results for beta over HN that I showed you before. Another nice feature of this scenario and the fact that there are first order phase transitions is the fact that primordial black holes are also produced. One mechanism to produce these primordial black holes is the so-called late blooming mechanism. Let us discuss it because it is a quite model-independent mechanism that, to some extent, is always there in first-order phase transitions. And it is basically based on the following observation. Since the bubble formation process is statistical for both quantum and thermal reasons, distinct causal patches can undergo phase transition at different times. And patches where the phase transition occurs at the latest time undergo the longest vacuum-dominated stage. And so basically in these late blooming patches, there is an overdensity. There's some mass excess that, if large enough, can trigger the collapse into primordial black holes. Now, one feature that we'd like to discuss here is the time dependence of the false vacuum decay rate, what I call gamma V. One reason why I want to do this is because it's a key information to compute primordial black hole production. Now, you can expand gamma V for a time around the nucleation time, when the temperature was equal to the nucleation temperature by definition. And the reason why I expand around this time is that for previous times, essentially the phase transition was not effective. So from this time on, you can do a Taylor expansion and obtain this relation where I expand in this way conventionally. And beta is exactly the inverse duration of phase transition that I showed you before, while beta 2, beta 3, etc. are other coefficients of the Taylor expansion. Now, if you neglect beta 2, beta 3, etc., you get this relation, an exponential relation between gamma V and time, which is a relation that is commonly used without justification. But what we will show is that this approximation is actually valid in the phase transition with radiative symmetry breaking, which feature a large enough of supercooling. So exactly the case in which we can use the model-independent approach. To show that, let us give you some detail about the the late blooming mechanism in a simplified approach in which we approximate the distinct causal patches of the universe as homogeneous and isotropic separately. And so we will have some Friedman equation for the late blooming Hubble patch. Here, rho V is the vacuum energy density, A is the scale factor, and the label L corresponds to the fact that we are focusing on a late blooming patch. And for the rest, we will imagine to make some average, getting what we call the background. So we will have some background Friedman equation. So just like this one, but with the other rho R, rho V, and A, which are labeled by B because this is the background. Now we can solve these equations with respect to rho R and A, substituting to rho V this expression here. Delta V is the difference in vacuum energy density defined before, and F is a function of two variables defined here, where this R of T and T prime is given by this relation in our scenario. And T and I is the instant when the first bubble forms in the ith patch. Now, the mass excess, that is an important parameter to determine when primordial black holes are produced, can be defined as the difference between the late blooming and the background radiation energy density divided by the radiation energy density in the background, where this rho R I, T, and Tni, because you see that there are two arguments, are the solution of the previous Friedman equations that are shown at the beginning of the slide. for the time t, generic time, and tni as the instant when the first bubble forms in the ith patch. Also, in the next slides, we will call T max the value of T when the mass excess is maximal, the maximal of delta for a given TNI. And TNI PBH is the minimal value of TNI such that this mass excess equals some critical value for primordial black hole production. This critical value is not known exactly. There are papers quoting the value of 0.45, but this is debated and it can vary very well by some decimal. I mean, can be 0.6 very well. And so we'll use this 0.45 in the next slides, but keeping in mind that other values are possible. And so this is the evolution of the scale factors and the Hubble rates as a function of time. Actually, in the plots, I'm using the dimensionless time t over Tec, where Tec is the time which the temperature equals Tec. And h hat is a dimensionless value of the Hubble rate, defined in terms of the Hubble rate by this relation, and r hat h is a dimensionless Hubble radius that is defined by this relation. The important point of this slide is the fact that the time variation that is important for us between tau n, which is the tau corresponding to Tn, the nucleation time, and tau equal to tau max, the time corresponding to the maximal value of the mass excess is, you can see, is of order 1. So the time variation in units of Tec is of order 1. And the same is true also for the energy density. Here I'm plotting the dimensionless energy density rho hat, which is defined in terms of the energy density by this relation, and the mass excess delta for delta C equal to 0.45, this typical value. And again, you can see that the time variation in unit of Tec is of order 1 for the relevant time range between tau n and the time at which you reach the maximum, that in this case is this quoted critical value for primordial black hole production. So now you can go back to the question of why you can use this exponential expression for the gamma v in terms of time. And again, we consider time which is close to Tn, not much smaller than Tn, sufficiently close or bigger than Tn. Because for T much less than Tn, anyway, the first transition is not effective, as I said. But also you have to assume that the vacuum decay has not occurred yet, because otherwise it would not make sense to compute a vacuum decay probability. So the universe is exponentially expanding, and the Hubble rate is then given by for any time that is relevant here is given by what I call hi, and it's constant in time. So the temperature exponentially drops, and now you can substitute this relation in the expression for the S3 over T, which is the action of the bounce. And let us consider first the supercooled expansion of leading order. You get, in this case, this relation. A prime, hi, and x are time independent. I've already defined h prime and hi and a prime. X is just the logarithm of chi0 over Tn. They are time independent. So the time dependence comes from here. Now you can insert this result in the expression for gamma v, because what we want to do is to see how gamma v depends on time. What you get is this expression here. Tn is, of course, time independent. A prime, hi, and x, I recall, are time independent. So the time dependence comes from these two terms. And now if you expand for t around Tn, the first term in the exponent, you get a Taylor expansion, and you can show that the first two terms in the Taylor expansion, this one and this other term here, simply reproduce the exponential law that I showed you before. So the question is whether these Taylor corrections are small. But what you get is that this quantity that appears in the powers of the Taylor correction, it is essentially a geometric series. And this quantity can be written in terms of the dimensionless time tau, which is t over tx, with this relation, and x. Now, gamma is a quite moderate factor, is not large, 0.7 something. Also, square root of 3 gives a further suppression, but the important point is that x is rather large in the supercooled expansion, because x is the logarithm of chi0 over Tn, and since epsilon has to be of order 1, it turns out that, or much less than 1, it turns out that x has to be very large, at least of order some tens or even 100. And so because the time variation in units of the EC that are relevant for primordial black hole production are of order 1, as I said before, then this factor is always small. And now you can go also ahead and compute corrections to this estimate and go to the improved supercooled expansion. But because x always remains rather large, at least of order of some tens, this factor remains small, and the exponential approximation for the decay rate in unit of volume remains valid. Now, how long the field is trapped in the false vacuum? This is an interesting question because the number of e-folds that basically is a quantity that parameterizes how long the inflation lasted is an important quantity in cosmology, and it is something that is constrained. Now, the number of e-folds in this kind of thermal inflation, because we know that although the temperature is quite small, it is not exactly zero. It is because of the temperature that we have a barrier. So we can call it thermal inflation. The number of e-folds, how long the inflation, thermal inflation lasted, is given by this relation here, the logarithm of Tx over Tn. Okay, now this is a generic result. It is valid when the space-time curvature is negligible in the phase-time phase transition process, but it is also valid when the space-time curvature becomes important. What I've said so far, basically, it is only valid, basically, it assumed that space-time curvature is negligible in the phase transition process. But let us speak about a little bit of the role of space-time curvature. In general, we can also add a non-minimal coupling between the field chi and the Ricci scalar R. This is compatible with classical scale invariance because the corresponding coefficient psi is dimensionless. Now, we can have two regimes. In one regime, we can neglect the curvature of Tn, and this is valid when Tn, the curvature, sorry, with respect to Tn, when Tn is large enough compared to the typical curvature scales. Okay, and this is the case that we have analyzed so far. But there are cases in which Tn can be comparable to the curvature scales. Now, if it is negligible to the curvature scale is negligible with respect to the n, then the size of the bounce, because the bounce represents some bubble inside a false vacuum, and basically smoothly interpolate between the false vacuum and the true vacuum. If the size of this bounce solution is much is the size of the bound solution is much smaller than the inverse quantity that appear here. So m that turns out to be a word of the inverse of the bubble size is much bigger than this quantity here. The curvature is negligible. This relation comes from the fact that basically this non-minimal coupling produces a contribution to the effective mass of chi. So which is given by this first entry in the max. So when this contribution is small, corresponding to the effective mass that is there for thermal reasons, then you can neglect the curvature. This other entry comes from the fact that curvature also appears in the fact that the zeta space has a finite volume and a finite size, which is precisely given by hi over pi. However, there can be cases in which the m is not large, correspond to this max, and then in this case, we can always favor the phase transition completion by taking psi bigger than 0 in a way that the barrier essentially is reduced by this non-minimal coupling here. And the number of e-folds in this case is at least approximately given by the value of the temperature such that basically the logarithm of Tx over T, where now T is the value of the temperature when the barrier disappears completely because of the contribution of this non-minimal coupling. Now we can also discuss reheating after all this inflation. So when the temperature drops by many orders of magnitude, you need to reheat the universe. And there are two cases. One is the case in which the standard model is inside the radiative symmetry breaking sector. And in this case, we have essentially by definition sizable couplings between chi and the standard model particles. So standard reheating can occur through decays of chi into standard model particles. Essentially, what happens is that the energy density after inflation is stored in chi and then is released to standard model particles to decays of chi. Here we see how the decay rate of gamma of chi into standard model particles behaves as a function of sin alpha, where alpha is the mixing angle between the Higgs and chi. And V here is the usual standard model VEV. Another case is when the radiative symmetry breaking sector is a dark sector weakly coupled to the standard model. In this case, we found that reheating can occur if you include a dark photon in the radiative symmetry breaking sector with kinetic mixing with the standard model photon eta, given here, and mass md. And basically the white region here corresponds to the case in which you have efficient reheating, which is quite fast in the sense that I defined before, where the pink region corresponds to slow reheating. Okay, let us conclude then standard model extensions or dark sectors, because we have both possibilities with radiative symmetry breaking, where symmetries are broken, masses are then generated radiatively, feature strong and long first-order phase transitions. An advantage is that you have high predictivity because only marginal operators are allowed. And a motivation is that this kind of theories lead to observable gravitational waves and also primordial black holes. We discussed a model-independent approach to study phase transition in this scenario, which can be adopted if supercooling is strong enough in a precise sense that has been specified, and also fast reheating after these supercooled phase transitions are possible. Thank you very much for your attention.
Thank you so much for your very informative talk. And now
Thank you.
questions for Professor Salvio. Suggestion for a work of master thesis in this.
Sorry, you're frozen now. Can you hear me? You can hear me? Okay. So it's just Angelo was frozen. Uh-huh. And now he disappeared. Okay.
Sorry, I have a very bad connection in this moment,
No
so
problem, no
that's
problem.
why I'm. Please, please, Christian, please.
Yeah, so basically, in this theory, you have quality couplings essentially at leading order in the potential. And so since you have four fields, three of these can be the Higgs boson, and one of these can be delta chi, the fluctuation of chi around its valve. And so we computed this decay rate into three Higgs bosons in this generic scenario, and we plotted how it behaves with respect to the mixing angle. So the origin is the quartic coupling that can then be expanded around. So one of these fields can be chi, and the other three can be the Higgs boson. Yeah, yeah, it's a three-level decay. Yeah, three-level decay. Yes, it is three-level. Yeah, no problem. Angelo, were you asking something before? Oh, he's frozen again. Okay. Oh, you're
So,
back.
yeah, I'm very sorry. I mean, it's better to stop here because I'm at
Can you hear me?
So yes, yes. No, no. Let's stop here. I mean, if we
Okay.
have other question, we will contact you
Okay.
privately. So thank you so much. Really, thank you for your great effort and your amazing talk.
Thank you very much for the
Bye bye.
invitation. Okay.
Okay. Bye bye.
Bye.
Ciao.
Ciao. Thank you.